Okay, and we'll go from current slide. All right, as I said before several times, one of the main changes that made from the previous edition to this edition, the chapters became topics, okay? So you bought new books to get that, okay? But last time we just finished chapter 15, we did the lab, we got the test. Tia, you got both of those, right? The chapter 15, lab and test last time, right? Okay, good. All right, now, sorry about last Monday. I found out Thursday that a meeting that I said I had an interest in going to, if we took advantage, there were three options. I said if we go for the one in Atlanta on a Friday and Saturday later this month, I said that would be great. Well, they contacted me back and said, well, we're going to try for the one in New Orleans. I said, but that's on a Monday, Tuesday. I've got classes. Well, yeah, I mean, we still want you to go. But we may still wind up with one in Atlanta on Friday, Saturday, so don't worry. Well, I found out last Thursday that they got the one in Atlanta Monday and Tuesday. So I couldn't give you much notice. If I'd only been thinking well, I would have, on the first email, said, go to Dr. Bryant's class, because they're doing almost the same stuff. They start a little different time, but you could have done it. It wouldn't have been any problem. But I sent the wrong email first saying the class was canceled because I thought all my classes were, and I thought, wait, now physics don't have to be, so I sent the second one, but I don't know if anyone saw it. I know that none of you attended, did you? Dr. Bryant's class on Monday?
No, most of us don't get off work until 5, and his class started at 4.
Yeah.
And so out of like the 6 of us, like 4 of us had work till
right.
then.
Okay.
And so like.
All right, well, we'll pick up and go in topic 16 here, electrical energy and capacitance. Okay? Any questions on the first two topics, 14 and 15? Okay. Here's 16. Now, in your Physics 201, when you had that, you last summer, I don't know when you had it, okay, potential energy. The concept of potential energy is useful in the study of electricity. A potential energy function can be defined as corresponding to the electric force. Now, let's do a flashback to mechanics, 201, okay? A force and energy. Tell me the difference between the two. Generally. A force is a vector. Energy, a scalar. Okay? Unit-wise, they're very close, though one unit off can make a lot of difference. Energy is force times the displacement. And here's making. Okay? So, the units for force would be kilogram meter per second squared. For energy would be kilogram meter squared per second squared. Okay? So again, they're somewhat related, but they are quite different. So a potential energy function can be defined corresponding to electric force. All you have to do is multiply a distance by it. Okay? In kind of a scalar type way. Okay? As in a dot product. Electric potential can also be defined. Potential energy is defined, but we can also identify electric potential. The concept of potential relates to circuits. Okay? I think it relates to more than that, but for their purposes here, it relates to circuits. Okay? So, let's take a look at first electrical potential energy. Now, again, a flashback to 201, mechanics. We had two different kinds of forces. lots of ways to classify them, but one is conservative forces via non-conservative forces. For instance, conservative forces, gravitational force is typically a conservative force. Non-conservative, friction is almost always non-conservative, okay, force. So, we have two types of forces, conservative and non-conservative. The Coulomb force that we used last chapter is a conservative force. Now, what does that mean? It is possible to define, what a conservative force is, it doesn't matter the path you take, your change of energy is going to be the same. Kind of. I mean, that's one way to look at it. So the second bullet here, it is possible to define an electric potential energy function with that force. That's because it is a conservative force. Just like gravitational force is a conservative force, therefore you can have gravitational potential energy. Okay? mgh as opposed to mg. Okay? So again, very, very similar. Work done by conservative force is equal is equal to the negative of the change of potential energy. Okay? Now that hopefully sort of makes sense to you. Let's do the gravitational. Okay? The work done that I'm doing on this book to raise it up here, okay, obviously I'm doing work to make it move, right? Having to do work. Well, its gravitational potential energy is increasing that. But I'm doing work on it. If the gravitational potential energy was doing work on the book would be falling. Then the change of potential energy would be decreasing as the conservative force, gravity, is doing work on the book. So therefore, the work done by the conservative force, gravity, is equal to the negative of the change of potential energy. Same thing with electrical forces, the Coulomb force. Remember, if we had a charge up here, you want it to be positive or negative? I don't care. Positive, okay, a positive charge up here. Okay, I'm going to do work to bring in, okay, let's just say we have another charge here. What kind of charge do you want this one? Positive or negative? Positive. Okay. If I'm going to bring this positive charge closer to this one, then I'm having to do work on it. But the conservative force is doing work against me, so the work done by, you can look at it the same way you did gravitational potential energy. Okay? The work done by the conservative force is equal to the negative of the change in potential energy. If I increase the, and we haven't defined it yet, the potential energy of that positive charge that I brought in, then I'm doing the work done by the conservative force would then be equal, would be the negative of that. Okay, here maybe we'll see it better. This is figure 16.1, bottom of page 527. Work and potential energy. We have here two parallel plates. We introduced that concept last chapter, you know. Because the field between two parallel plates is generally uniform, and so it's a nice, predictable field to have. So, because we have two parallel plates, one positive, one negative, there is a uniform field between those two plates, represented by the orange lines here. There's a uniform electric field between those two plates. Always going from positive toward negative. Uniform, evenly spaced, okay? As the charge moves from point A to point B, work is done on it by this field. Now, they didn't say what kind of charge that was. I'll tell you, it had to be a positive charge, okay? If work was being done by the field, because the field is pushing a positive charge in that direction. So if work being done by the field, positive work being done by the field, this would have had to been a positive charge being pushed from there to there. Okay? Oh, they show it here. There's the positive charge. I thought that's just position. There's the charge. Okay. Work is being done on it. So the work to go from A to B is the force in the x direction times the displacement. That's the definition of force, work. Work is force times displacement. Here's the other definition. Force, Coulomb force, Q EX, that's the Coulomb force, okay? And then the delta X is X final minus X initial, okay, the difference between B and A. The change of potential energy is the opposite of that work done, so it's minus QEX. Then they went back to delta X. While they were going back and forth, but it's fine. Only for a uniform field for a particle that undergoes a displacement along the given axis. This works for that situation. In other situations, yeah, you have to deal with those. Okay? The SI unit for energy is the same as it was in mechanics, a joule. And a joule is force times the displacement, Newton meter. Also is force per unit charge, that's what Newton per charge, times the charge, that's a Newton, times the displacement here too. So both of these have units of joules. Does that make sense? Units are your friends. If you keep up with them, generally you're going to be in pretty good shape. Okay? Now, this is leading to something not unique, but very much used in electricity, electrical physics, okay? Is the concept of potential difference. The electrical potential difference, and we give the symbol delta, that's difference, V, okay? This is one of those rare circumstances where your parameter they use is capital V for potential difference, okay, delta V. The unit for that is also capital V, voltage, okay? One of the few times when the parameter and the units are the same. So you use capital V for both. The potential difference, electric potential difference, delta V, between 2 points A and B is defined as the change in the potential energy, that's final value minus initial value, of a charge Q moved from point A to point B divided by the size of the charge. So here is a key formula. Potential difference, delta V, is equal to VB minus VA. That's exactly what we mean by a potential V difference, a difference between these, B and A. And the definition for that is change of potential energy per unit charge. So, well worth your while to get this sort of implanted in your brain. Potential difference is energy per unit charge. Energy per unit charge. Okay? That's your potential difference. Potential difference is not the same as potential energy. Potential energy is the numerator only. Per unit charge, that would be your potential. Now I'll turn that around, multiply both sides of that. Q delta V would be your change of potential energy. But they're not the same. They differ by the unit of charge. So you don't really have anything quite similar to that in mechanics. I mean, similar, but not quite the same, because you don't have units of charge. So let's continue with that. Another way, and this is what I just said, to relate the energy and potential difference, multiply both sides by Q, and you have the change of potential energy is the charge times the change of potential difference. Both the electrical potential energy and the potential difference are scalar quantities. Forces and fields are vector quantities. Potential energy, or any kind of energy, and potential difference are both scalar quantities. The units for the potential difference, as you noted before, was joules per Coulomb. So your voltage is joules per coulomb, energy per unit charge. A special case occurs when there's a uniform electric field. Special case, uniform electric field, then that potential difference will be change of that field, the negative of the field times the displacement. Now this is only true for uniform electric fields. It's kind of like those kinematic equations you had in 201. They were only good for uniform acceleration. This one's only good for uniform electric fields. The delta V is minus E sub x times delta x. Okay? It gives more information about the units. Okay? Well, the units are still good. Remember up here we said joules per coulomb. Okay? Well, here we have volts per meter. That's another unit for electric field. Before we were using electric field newtons per coulomb. Now we have volts per meter. So these are interchangeable units, newtons per coulomb or volts per meter. Either one of those are good units for electric field. Most of the time we use newton per coulomb, but there are circumstances where volts per meter probably is going to come in more handy. All right. So continuing, now potential energy compared with potential. We did a little bit before, but here's some more. Electric potential is a characteristic of the field only. The electric potential is a characteristic of the field only, independent of any test charge that may be placed in the field. Remember, okay, get this now. A force is that Q, Coulomb's constant, KE times charge divided by distance squared. Divide that by your test charge, and then you get electric field. Okay? So the test charge has been divided out. So therefore, it's independent of any test charge that may be placed in the field. Electric potential has nothing to do with the test charge. The electric potential energy is characteristic of the charge field system. You have to have the charge there, you have to have the field there, due to an interaction between the field and the charge placed in the field. Whereas electric potential doesn't have that charge dependence. You've divided that out, energy per unit charge. Okay? Units, again, are helpful there. Okay? How about electric potential and charge movements? Now, let's say that we have our good old parallel plate. Okay? One positive, one negative. Uniform field in between, from positive toward negative. Okay? If you were to deposit a positive charge anywhere in that field, where is it going to go? Away from the positive toward the negative, right? Repelled by the positive, attracted by the negative. It's going to accelerate, not just move, accelerate spontaneously from regions of high potential to regions of low potential. So when released from rest, okay, negative charges, though, are going to be accelerated from regions of low potential to regions of high potential. Now, this is a little unique, okay? In most of physics, you just have high potential, low potential, okay? And objects always move Brianna, right? Okay. I was just saying earlier, I have a Brianna in my last class. I have two Courtneys in my last class, so I have to stop and think, okay, which class, which Brianna, which Courtney, okay. And then, of course, I have Tia in two classes, one earlier today and one now. And I have Shakina in two classes and F.A. in two classes. In fact, Shakina's in 3 classes.
Can I go ahead and get my test in the lab before I forget?
From last time?
Yes, sir.
Okay. Let me get it for you. What's that? Okay.
Test 2.
Lab.
And we're turning test 1 in today?
Test. What's that?
We're turning test 1 in today?
That'll be fine.
Okay.
And if you're okay.
Here's test 1.
Okay, here's test 2.
Thank you.
Thank you. All right. All right, good deal. Okay. All right. What I was saying before, in most of physics, we don't have, I don't know if this is quite right, but in a lot of physics, we don't have opposite bodies, like positives and negatives, and we usually have just masses or other things without being 2 different ones, okay? So therefore, in most of the rest of physics, objects always move from areas of high potential to low potential. However, because of electrical systems, you have 2 different kinds of charges. And if a positive charge is going to move from high potential to low potential, therefore a negative charge has to go the opposite direction. So this is sort of unique, I won't say totally unique, in physics where an object goes from low potential to high potential, but that's because it has a negative charge. Work must be done on a negative charge to make them go in the direction of a lower potential. You have to force it to go in that direction of lower potential. Okay? So, let's look at electric potential of a point charge. Okay, the point of 0 electric potential is usually taken to be somewhere way out there at infinity. Infinite distance from the charge. So, I think y'all said this is a positive blob of test charge up here. A charge here. Source charge. Okay? You'd have to go all the way to infinity and beyond. No, to infinity. And there you would have your potential from that charge to be 0. Okay? Now, any place that you bring it in, the potential created by a point charge Q at any distance r from the charge, say if you brought it from infinity to say here, however far that is from your source charge, now your potential is V is equal to KE, good old Coulomb's constant again. We used it in forces, we used it in fields, here we're using it in potential. Actually, if you look back, you can use it in potential energy as well. It's KQ over R. Okay? KQ over R. Now, if you remember, let's start it way back. Let's just do a little move back. If this was a force here, that would be KE, same KE, Q times Q divided by R squared, but that would be a vector quantity. Okay? To get the field, we divide out one of those charges. That would be KEQ divided by R squared. Okay? Potential energy, go back to the force, KEQ squared per R squared, multiplied by a R, wipes out one of these, that gives you potential energy. Okay? Divide that by Q, and that gives you your potential. Okay? So the four forms of those major things we talked about, forces, fields, vector quantities, potential energy, and potential scalar quantities, they all start at almost the same place, but they just have different powers of Q's and R's. Okay? So potential energy created by point charge Q, any distance from the given charge would be this. That's energy per unit charge. You're dividing out one of the charges. Okay. Now, the electric field and the electric potential depend on distance. However, they're different distances. Electric field is a 1 over r squared dependence, whereas the electric potential is proportional to 1 over r. Okay? Now, these are quite different curves, and you can play around with them and see, but remember the other big difference? This is a vector quantity, that's a scalar quantity. But we're talking magnitudes here, and that's indeed what we've got. Field and potential are related to each other. How are they related? Field is equal to voltage per meter, volt per meter. And you see that from these equations pretty nicely. Okay. Now, what if we're talking about the electric potential evaluated? Welcome back. Sam is here. And I'm just sort of making an assumption here. None of y'all showed up for, I talked with some people here early, for the other class, the 214 class, did you? I sent that email announcement after I realized, wait, I didn't have to cancel the physics classes, I could have put them, but I understand that some of you couldn't have made it anyway because of the start time. Okay. The electric potential of multiple point charges. Again, the superposition principle applies. It applied to forces, it applied to fields, it applies to potential energy, and it applies to potential. Superposition principle applies. The total electric potential at some point P, wherever it happens to be, due to several different point charges, is the algebraic sum of the electric potential due to the individual charges. It's not quite the same as the superposition principle of forces and fields. What's the difference? In forces and fields, it's the vector sum. Potentials and potential energy, algebraic sum. Easier to work with. The algebraic sum is used because potentials are scalar quantities. You don't need to worry about direction. They just add the algebraic sums together. Okay? Now, good attendance tonight. Except for the two folks who were here earlier and left. Oh, you're back. Good. Glad you made it. Okay? All right. Even half dozen now. All right. Now I'm trying to find this in the text. I think, I'm not sure, but I think they took this one out. No, they didn't. Okay, sorry. Okay. Let me back up a little bit. I skipped over a quick quiz. I know how much y'all enjoy your quick quizzes, right? All right. Backing up a little bit, if an electron, what's an electron, by the way? Tell me a few characteristics. It's a negative charge. That's the main thing. If an electron is released from rest in a uniform electric field, Does the electric potential energy of the charge field system increase, decrease, or remain the same? If an electron is released from rest in a uniform electric field, does the electric potential of the charge field system increase, decrease, or remain the same? Okay? Okay. Any guesses? Increase, decrease, or remain the same? If an electron is released from rest in a uniform electric field, does the electric potential energy of the charge field system increase, decrease, or remain the same? Okay, you said remain the same. And this, by the way, is under topic 16. Used to be called chapter 16, but now topic 16. Big change, that's what you paid for. Okay, and this is 1. And they say no. They say B. Decreases. Okay? Here's the difference. Your answer would have been right if this word here had been left off. The electric potential, in the book, the electric potential of the system would remain the same, but the electric potential energy would decrease because you released a negative charge into that field. Now that becomes part of the system. Okay, so therefore it is a decrease. Again, that's a little on the tricky side, but they seem to like tricky. All right, that covered through electric potential. All right, there is a little tip here, and I think maybe we've already hit it. Yeah, here it is. Electric potential is characteristic of the field only. So there, the presence or absence of a charge wouldn't have made a difference. That would have remained the same. Independent of the test charge that may be placed in the field. On the other hand, potential energy is a characteristic of the charge field system due to an interaction between the field and the charge placed in the field. So that's what decreased it from before. All right. Now, quick quiz 16.2. I wish I had the graph here, but they don't, okay? If a negatively charged particle is placed at rest in an electric potential field that increases in the positive x direction, the field is increasing in the positive x direction, okay, of the potential field, okay? Will that particle accelerate in the positive x direction, accelerate in the negative x direction, or remain at rest? If a negatively charged particle is placed at rest in an electric potential field that increases in the positive x direction, will that particle accelerate in the positive direction, accelerate in the negative direction, or remain at rest? Okay? You try again, but it's not. It's going to go one way or the other. Okay. You say it goes in the positive x direction. Okay? No, let's take a look and see. This is, no, we're going to try to explain it. Okay? It does accelerate in the positive x direction, and here's why. Very good. Okay, here's why. Okay, remember we said the field is increasing in that direction. Field is increasing. Okay, a positive charge would then have to move this way because the field is getting greater that way, meaning the positive field is a negative charge, which is what is stated, is going to be attracted to that. So that will accelerate in that positive direction. Okay? Now, 16.3. They have a graph here, and most of you have your books or something to look at. Okay? Since I'm not sure you do, let me kind of draw this graph. Let me get my pen activated for a darker color. Okay? Here is going to be, now this is voltage this way, displacement in this way. Okay? This comes up and does that number there, dips down here, comes back up, has a pretty high peak here, and heads down. We don't know where it goes from there. Okay? Here's point A, and here's point B. Okay. Obviously, voltage is positive up here and negative here. Pretty standard. So this figure that I've drawn here, you see in your book, is a graph of an electric potential as a function of position. If a positively charged particle is placed at point A, okay, what will its subsequent motion be? Will it go to the right, go to the left, remain at point A, or oscillate around point B? Okay? If a positively, say again, it will go to the left because this is a positive potential here, and we said it's a positive charge, didn't we? A positive charged particle is placed there. It's got to move from high potential to low potential, so it's got to move to the left. Very good. Okay? Just make sure the back of the book agrees. That's B moving to the left. 16.4. If a negatively charged particle is placed at point B, in figure 16.3, which is the same figure, given a very small kick to the right, that way, what will the subsequent motion be? Well, it goes right and not return, go left, even though you kicked it to the right, remain at point B, or oscillate around point B. Say that again. No, a negative charge. If a negatively charged particle is placed at point B, and B is directly under the peak, okay? Okay, yeah, you push it to the right, so it'll go there. Does it stay there? No, it's negatively charged. If you force it to go this way, then you moved it toward an area of lower potential. It's going to try to come back here. It will overshoot, and it will go back and forth. So a lot like a spring, okay? It will oscillate back and forth, or at least that's my impression. Let's see what they say. 4 is D, oscillate around point B. Okay? It was very happy just to sit there at point B, because that's the highest potential it was. But when you forced it out of that, then it oscillates back and forth and back and forth. All right. Now, I think finally we're ready for this dipole example. Okay? This is electric potential and potential energy of point charges. Okay? Let's go back and just review what we've just recently done. There is the graph that's the top of page 534. There is the formula just below that on 534 that we were dealing with. And now we're ready to do this at the bottom of the page. This figure is a computer-generated plot of the electric potential associated with an electric dipole. Someone remind me, what is an electric dipole? It doesn't have to be moving. It can be stationary. But dipole, meaning it has two poles, right? Di means two. And for that to make sense, say again? One negative, one positive. Okay, just looking at this, what would you think, where do you think the negative would be? Okay, it would be right here. Its negative field is down here. The positive would be here. Its positive field is indicated there. Okay? These are electric potentials. Okay? So that would be your dipole. Okay? Now, the potential is plotted on the vertical axis in arbitrary units. These don't have to be volts. It's usually what we use for potential. But these are kind of arbitrary units, so they don't have to be 2 volts or minus 2 volts, or whatever. Okay. The two charges have equal magnitudes, opposite charges. Okay. That's why they go up as far as the one on the left, down as far as the one on the right. It is an example of superposition because if you didn't have the one here, then that probably would be even taller, okay? But this is pulling it down this way, especially in here. You can see the lines of force that are going basically straight from there to down to here, okay? So that's, I don't think it's a great example of superposition, but it is an example of superposition, okay? They just showed that, and that's all there was, okay? I guess that was their identification of superposition. Yeah, okay. Now, this is the figure on page 535, okay? V1 here is the electric potential due to a charge, positive charge at Q1 at some point P, okay? So, here's charge Q1, positive charge here, our distance from that point P, the potential at P due to that charge, only this charge, is your QE times this charge divided by the distance. Remember, potential is dependent on distance of the first power, whereas fields and forces are the distance square, inverse square laws. Okay, this is just inverse proportion. Okay, the work required to bring Q2 from infinity to that point P without acceleration. Okay, so you've got to bring that point from way out there in infinity, bring it here without accelerating it, not letting it accelerate, but you're having to bring it there without acceleration. Then what would that be? Okay, you'd have the work required. Remember, work is, the opposite of the potential energy change. The potential energy change would be the product of the potential there, that's this part, times this charge that you brought in there, okay? Still divided by R. We're still dealing with potential energy, okay? Because it's a change of potential energy. So therefore, that would be the work required to bring it in from infinity to there without acceleration would be a positive amount of work, because you had to do work to make that come in closer to another positive charge. That work is equal to the potential energy of the two-particle system, which is exactly what is stated there. Okay? It's KE, Q1 over R, that was the potential there, multiplied by the second charge. Okay? So that was the work, change of potential energy, which is also the work that was required. Okay? That leads to quick quiz 16.5. Consider a collection of charges in a given region. Suppose all other charges are distant and have negligible effect. So you just have a collection of charges here. Everything else is so far away it doesn't have any effect. Okay? Further, the electric potential is taken to be zero at infinity. That's what we usually do. If the electric potential at a given point in the region is zero, which of the following statements must be true? Now, the region that we have all these charges, it says the electric potential at that given point in the region is zero. Which of the following statements is true? Must be true. A, the electric field is zero at that point. Okay, in other words, just because the potential is zero there, does that mean the field is zero there? That's what it's saying. B, the electric potential energy is a minimum at that point. C, there is no net charge in the region. D, some charges in the region are positive and some are negative. E, the charges have the same sign and are symmetrically arranged around a given point. Okay? Which of those do you think would be true? Electric field is zero at that point. The electric potential energy is a minimum at that point. There is no net charge in the region. Some charges in the region are positive, others are negative, and the charges have the same sign and are symmetrically arranged around the given point. So in other words, you have a collection of charges that are symmetrically arranged around that. Now this is not the figure for it. I don't think they have a figure for it. So I just left that one up. Which of those do you think is true? A very long question. Do any of you have it in your book so you can look at it and give your opinion of the answer? This is 16.5. The one that must be true, and you can almost see it back here. Okay? Right in here, you have zero potential. Okay? And why you do, some charges in the region are positive, some are negative. So there has to be some place in between there where the potential is very positive there, very negative there. Somewhere in between it has to be zero, which means that some charges in the area had to be positive and negative. They don't have to be symmetric like this, because if you had a +2 here and a -3 over here, then that point would be closer to the point 2 further from the -3, but you would have to be somewhere in between the two. So the only one of those that would have to be true is that D. Some charges in the region are positive, some negative. Okay? The reason the electric field doesn't have to be zero if you have all those charges around, the likelihood of the electric field being zero is pretty slim. I mean, especially if positive and negative charges. the field is definitely pointing from the positive to the negative. So the likelihood of that being zero, very, very low. In fact, I don't think it could be. So A would be out. B, the electric potential energy is a minimum at that point. No, the electric potential energy would probably be negative at a point closest to the negative charge. Okay? In fact, probably right on it or someplace in between them. Okay? So that would probably not be true. C, there is no net charge in the region, or you're given that you had a collection of charges in a given region, so how can you say there's no net charges in the region? Okay? If there were no net charges, yeah, then it probably would be true, but that doesn't have to be true. And D, there's the one that's correct. Some of the charges in the region are positive, some are negative. And E, the charges have the same sign, are symmetrically arranged around the given point. That would just be building up a positive potential. It wouldn't be negating. Okay. Let's look at 16.6. I'm afraid it's almost that. It's not quite as long. A spherical balloon contains a positively charged particle at its center. As the balloon is inflated to a larger volume, while the charged particle remains at the center, sorry, sorry, which of the following are true? Now notice they said which are true, indicating, not guaranteeing, but indicating that more than one are true. A, the electric potential at the surface of the balloon increases. What you think on that? True or not? I would say not, because all you're doing, you've got the charge in the center. This doesn't change. This is getting larger, so if anything, the potential would be decreasing. As the balloon is getting larger, the charge isn't changing any, so your potential would be, if anything, decreasing. So A is out. B, the magnitude of the electric field at the surface of the balloon increases. I think not, because if it's a spherical balloon and getting bigger, at any place on here, those are getting further and further apart, so therefore the magnitude would have to be decreasing. So I think B is out. The electric flux through the balloon remains the same. Okay? Now it's been a while since we talked about electric flux, but remember, electric flux depends only on the charge inside, and if that hadn't changed, even though the balloon got bigger or smaller, electric flux remains the same. So I think it has to be C. Let's see what they say. And then they say none of the above, so I don't think that's it. 16.6, sure enough, is C. Now, all right. Now, these are just a couple of notes. We may have already passed them. I just didn't go to the slide in time to look. Additional notes about electric potential energy of two charges. If the two charges have the same sign, the potential energy is positive. Now, that didn't say they were both positive charges. They said if they have the same sign, the potential energy is positive. Positive work must be done to force the two charges near to one another. They have to have a positive thing. Two positives, two negatives, if they have the same sign, the positive work must be done so the potential energy is positive. The like charges would repel each other, so to make them go nearer to each other, you would have to add work so the potential energy would increase. Second bullet. If the charges have opposite signs, the potential energy is negative because the force would be attractive and work must be done to hold them back, the unlike charges, from accelerating as they are brought closer together. So you have to do a negative amount of work. So the potential energy would be negative. You would have to do work on the system to keep them from colliding. Okay? So here are your problem-solving strategies for electric potential measurements of point charges. As in every one, draw a diagram. Draw. Note the point of interest, that may be someplace there is no charge, or there is, it may not be, and locate from that point of interest the distance from each charge to that point of interest. Okay? Figure out where those charges are, and all you're really interested in is the distance. Okay? It doesn't matter direction, just distance. Then use the basic equation. Of course, V is equal to KE, that's coulombs or electrostatic constant, times Q, that would be the charge in question, and then divided by R, that's how far you are from that charge. Include the sign, okay? Now what that means is, of course, if it's a, you're having to do work to hold it, that could vary, so, but include the sign. The potential is positive if the charge is positive, it's negative if the charge is negative. So basically, if you let the Q carry the sign of that charge, then your potential will have the correct sign. Okay? So that's one place. Do let the charge carry its own sign. Okay? Now, if you have more than one charge, then do the same thing for every charge, but just add up the potentials algebraically. Don't mess with how far or anything else are. That's incorporated in the sum. Add those together. Signs do matter. Okay? So add the signs as well as adding the magnitude. Remember that potential is a scalar quantity. That's why you use the algebraic sum. There's no components to worry about. You have to worry about if this is a horizontal component, vertical component. There are no components. They're just numbers. So just add them together. But keep up with the signs. The signs matter. Okay. Now, there was example 16.4 there, and 16.5. If you need to see any of those done, I'll be glad to do them. I was hoping they were going to show at least one of those on the slide set, but they haven't. Need to see any of them? Okay. So let's move on to 16.3, which is potentials and charge conductors. In the new text, it says potential charge conductors and equipotential surfaces. Okay? Now this looks pretty familiar because we were doing the same thing with fields. Now we're doing potentials. All right. Remember what W is? Capital W? Work. Since work is minus Q times the voltage difference. Okay? It's the opposite of the potential energy difference, and that's exactly what this is. No network is required to move a charge between 2 points that are at the same electric potential. Great place for a diagram. I don't know if they're going to provide one or not. Okay? So the work is zero when these two potentials are at the same. So if you had an equipotential surface here, okay, and you have A here and B here, but they're at the same potential, then the work to move them there would have been zero because they have exactly the same potential. Okay? all points on the surface of a charged conductor in electrostatic equilibrium are at the same potential. Okay, so if you have a surface here, a charged conductor, all the points on that surface are at the same potential. Therefore, the electric potential is constant everywhere on the surface of a charged conductor in electrostatic equilibrium. As long as it's in electrostatic equilibrium, the electric potential is constant everywhere on that surface. Okay? And it basically goes back to the fact that the charge is evenly spread out on that surface. Okay. Here's one such surface. This is a conductor, and somehow you've managed to pile it up with a bunch of excess positive charges. So the conductor has excess positive charge here. All of the charge resides on the surface. It's a conductor, meaning the charges are free to move, so the charges move as far apart as they can from each other because they're all positives. But some of them just can't get away because some of the regions are pretty tight here, okay? So the field lines are going to be a lot closer here than they are down here or some of the other places, okay? Right. Now, all the charge resides on the surface. They all distribute themselves as evenly as they can, apart from each other on the surface, meaning no charges are on the interior, no charges are on the interior. The electric field, E, inside that conductor has to be zero, totally zero. All the charges on the surface and pointing in opposite directions, the field inside has to be zero. Anywhere inside has to be zero. The electric field just outside the conductor is perpendicular to the surface, as you see here. If this surface has a lot of curvature, there's perpendicular there. This is sort of flat, actually concave, so the fields are pointing inward here, convex out here, so they're pointing outward here. Fairly close to a straight line here, so they are parallel fields away. It's not exactly concave here, so they kind of point inward. Okay? Now, the potential is a constant everywhere on the surface of the conductor. All the charges required on the conductor, the potential is constant everywhere on the surface of the conductor. Even those places where it looks like those are fairly close to each other. What does that mean? These field lines are all the same length. They may be closer together, well, actually, potential everywhere, okay. We're talking potential, I was talking field. Potential is constant everywhere. The potential everywhere inside the conductor is constant and equal to its value on the surface. Whoa. The field is zero inside, but the potential is not zero inside. It's a constant and it's equal to its value on the surface. The potential. Not the field, but the potential. Okay? Notice from the spacing of the positive charges that the surface charge density is not uniform. Okay? Surface charge density not uniform, but the potential is. Everywhere inside is constant equal to the value on the surface. Potential is constant everywhere on the surface, so it's constant everywhere. All right. Now, sorry. May have, I did not break, but almost feel like I need to get some water, but let's see if we can move on a little bit more. The electron volt. What in the world do you think that is? Electron volt. By the way, the symbol is E, little e, capital V. Volt, capitalized, named after somebody, Volta, a Italian physicist. He did a lot of the early work with batteries and things like that. That's why they named the unit potential difference after him, volt. Is electron volt a potential measurement? No. Because volt is a potential measurement, electron, the E here, is a charge measurement. Charge times potential gives you energy. This is a measure of kinetic energy that an electron gains when accelerated through a potential difference of 1 volt. So 1 electron being accelerated through a potential of 1 volt, that would be 1 volt of kinetic energy. Okay? Then it would have, electrons in normal atoms have energies in the tens of electron volts. That's a bit standard. Excited electrons have energies of thousands of electron volts. The electrons that are up in these tubes being thrown back and forth and stuff, thousands of electron volts, maybe even higher. But the electron in just a normal atom, let's imagine this was aluminum, I think it is, not charged, not excited, electron there would have electron volts or energies of tens of electron volts. Okay? High energy gamma rays, those are the very deadly rays coming from the sun, coming from nuclear energy. Those have millions of electron volts. Okay? Now, electron volt, again, is a measure of kinetic energy. The amount of kinetic energy 1 electron would have when it's experienced the potential difference of 1 volt. Fairly small voltage difference, certainly small charge. Okay? So 1 electron volt is a tiny, tiny, tiny number of joules. 1.6 times 10 to the negative 19 joules. And a joule is already a small amount of energy. So this is really incredibly small, because this is an incredibly small charge over a voltage difference of about 1 volt. So it's got to be very, very small. Okay? Now, I just wanted to remind you, and I'm trying to recall where you're, nope. This book is different from several books in where they place the physical constants. Well, let's look at that 1.6. It shows up lots of places. Your elementary charge, 1.6 times 10 to the minus 19 coulombs. Multiply that by 1 volt. Volt is joules per coulomb. That gives you 1.6 times 10 to the minus 19 joules. So all these things do tie together and balance out very nicely. I think that's the only place that we see an elementary charge. Yeah, I thought maybe it would pop up somewhere else, but that's it. Okay. So that's an electron volt. Before we move to equipotential surfaces, here's another quick quiz. An electron initially at rest accelerates through a potential difference of 1 volt, gaining kinetic energy, Ke sub read that. My eyes. Ke sub e, okay, one electron, okay. Whereas a proton, also initially at rest, accelerates to a potential difference of -1 volt. Gaining kinetic energy KEP. Which of the following relations hold? Okay? The KEE, that's the kinetic energy gained by the electron, is equal to the kinetic energy gained by the proton. That's A. B, the kinetic energy gained by the electron is less than the kinetic energy gained by the proton, KEP. C, kinetic energy of the electron is greater than the kinetic energy of the proton. And D, the answer can't be determined from the given information. Okay? Which of those do you think is true? Electron volt is Q times V. Okay. Are the kinetic energies equal? Electron less than that of the proton? Electron greater than that of the proton? Or the answer can't be determined from the given information. All right. I hear nothing. What do you feel? Let me emphasize, we're only talking about energy difference, not speed differences, not anything except the energy, okay? And because of that, 7 has to be A. Same charge, opposite sign, but same quantity of charge, same potential difference. The KEP and KEE have to be the same. If we're talking about velocities of them, no, electrons move much faster. But the potential energy, same. All right. So that one was A. Let's move to equipotential surfaces. An equipotential surface is a surface on which all points are at the same potential. We've already hit some of those. Charged conductors, those are equipotential surfaces. Okay? These don't have to be conductors, but these are surfaces on which all points are at the same potential. No work is required to move a charge at a constant speed on an equipotential surface. If you have an equipotential surface and you can just move the charge around without accelerating or decelerating, that's an equipotential surface. Okay? The electric field at every point on an equipotential surface is perpendicular to the surface. Okay? Again, this could be an odd-shaped thing, but the fields, just like we showed in the previous illustration, the fields are perpendicular to the surface. Nothing too new there either. Okay? Now, the difference is these surfaces don't have to be real surfaces. They could be imaginary surfaces. Okay? the equipotentials for a point charge are a family of spheres centered on the point charge. Those are these dotted blue. They look here like circles. They're three-dimensional. They're actually spheres around there. And that surface is an equipotential surface. Because if this is a single, isolated, positive charge here, then the field lines emanate from that charge in every direction. Circular, radially, or three-dimensionally. They are emanating from there, evenly spaced, so therefore every sphere of whatever radius you get, that's an equipotential surface. It doesn't have to be a real surface at all, it just can be an imaginary surface there. The field lines are perpendicular to the electric potential at all points, and the field lines are shown in orange here, which I thought they were showing first, but they're talking about this first. This is what the field lines look like. If that's an isolated positive charge, they have to emanate away from that charge, evenly spaced, and therefore your spheres around that charge are equipotential surfaces, centered at the charge. Okay? All right. Now, what do we have here? Earlier you named it. Positive charge here, negative charge here. Every field line is connected to another one, meaning they're equal charges. Opposite signs, what do we call that? A dipole. That's an electric dipole. Now, that electric dipole is going to draw the, normally these would be spherically placed around there if that wasn't there. This would be spherically placed if this wasn't. But you have the other one here, so it's drawing these lines toward it, and these are being drawn toward it. So your strongest field are the places your equipotential surfaces are closest together. Okay? You can think of this as, if you've done any hiking in the woods and had a topographic map, the lines where the contour lines are closest to the other, those are the steepest. Okay? This is where the potential is going up the greatest, at the greatest rate. So the equipotential surfaces are closer and closer together here. Farther and further apart out here because the field lines are spreading out, and all these field lines are always perpendicular to their equipotential surface. Always. Here they're very concentrated, here they're very dispersed. So here these are not spheres anymore. They're sort of oblate spheroids, I guess you would say. They're kind of egg-shaped or something like that, or elliptically shaped. Okay? The equipotential lines are shown in blue again, the dotted blue lines. Electric field lines are shown in orange. The field lines are perpendicular to the equipotential lines at all points, always. Okay? But because these are attracted to each other, they're pulling together, so the equipotential lines tend to be closer and closer together. Now, this is an application of the principles we've been talking about. And they don't have a number on this slide. It's an electrostatic precipitator. Okay? This is used in real life, okay? Used to remove particulate matter from combustion gases. Okay? Particulate matter. Think of that as smoke. If you can see smoke, that means the little particles in it. Okay? You're trying to remove those from your combustion gases. This is reducing air pollution. It can eliminate approximately 90% of the mass of the ashes and dust that are given off in that smoke. Okay? This shows when a electrostatic precipitator is operating, and in your book you'll see another slide. Let's see if that's on the next slide. No, it's not. To the right of that, you'll see where it's not operating. Okay, you'll see the smoke coming out. The other thing this does is recovers especially your metal oxides from the stack, preventing those from getting blown into the atmosphere. So how does this work? Okay. What you have is a high voltage source here. This is shown to be sort of like a battery, but I don't think it has to be. Just some type of high voltage source. That this is the positive side, that's the negative side. Sorry. Your dirty air comes in. In the next figure, that air that was escaping, that's what's going into this electrostatic precipitator. Okay? What happens here is this is charged negatively, you see. It goes through the insulator so it doesn't lose any of the charge. It goes down here, and this weight is a negative charge. Okay? Now, your positive side is to ground here, which is a little on the unusual side. You usually think of the negative side to ground, but they've done this particularly. And that's connected to the outer surface here. Okay? That's all your positive charge. So the dirty air comes in, it's especially your metal oxides are going to be positively charged ions. They're going to be not right. Okay. Because you have, at least here it shows this is being negative, and a high potential difference between that and the walls here, you tend to get a discharge going. That's what it says here. The high voltage maintained in the central wires creates an electric discharge in the vicinity of the wire, so your electrons would be moving out here toward the positive. If they are, then they are going to pick up some of this dirty stuff that's in the air, and they're going to drag it with them to the outside here. Okay? And in dragging them to the outside, it then moves down, gravity pulls it out, and you dump the dirt out here. Dirty air in, dirt out. This is your ash, your dust, your metal oxides, whatever it is bringing in, because you have this high potential here, and that discharges in here, and as it discharges, then that is, they attach themselves to the particulate matter, and that gets attracted to the, and this is negative, that's positive, so it gets attracted to the positive side. Now, are these easy to operate? No, they foul up really quickly, especially if you have very dirty air coming in. You can saturate it in almost no time, and then they lose the effect. You have to keep almost pumping this dirt out, but you're trying not to lose your charge here, so you have to maintain, and this is why they're not super expensive, but there is an expense. You have to maintain that high potential difference across them. So there is a cost involved and a maintenance issue of trying to keep it clean enough that it keeps cleaning the air. And if you had a lot of pollution there, it can foul pretty quickly. Okay. It's also used in homes to reduce the discomfort in allergy sufferers. I don't know if you've seen any of these. They call them electrostatic air filters. Sometimes that'll be the name that's given. And they do the same type of thing, except now it's the allergens in the air. The pollens, the molds, the mildews, and things like that. They get plated out on the sides. But again, you have to keep collecting them and dumping them. Now, in a factory, those metal oxides may be used again, for something. They may be sold. Other things to do with it. What you do with the pollens and stuff that you get in your home, you want to throw those in the trash, okay? So every time you do to take these offline to do that, then you are no longer doing it. But they do work pretty well. But again, they use energy, and they have to be maintained pretty carefully. Uses many of the same principles as, electrostatic air cleaner uses many of the same principles as electrostatic precipitators, and they have the same problems. Okay? All right. Another application here. It wasn't all that long ago, in other words, during my lifetime, that a Xerox came out. Now, Xerox may sound like old technology to you guys, but I can remember when teachers and other people made copies by mimeographs. Okay? I don't know if any of you even remember what that is. I remember having to make things by you typing, before computers, typing onto a sheet that basically had a waxy substance. And when your type hit that, you made it thin there. Then you ran that through something, and the color, the thing that you were printing, the copies you were making, you were just picking that stuff up because the wax was an insulator, and where it was thin, it was a good conductor. That was basically what mimeograph was. The process of xerography, which is where the term Xerox comes from, is used for making photocopies. Much better system, much sharper system. It uses photoconductive materials. A photoconductive material is a poor conductor of electricity in the dark, but becomes a good conductor of electricity, of electric current, when a good conductor, electric conductor, when exposed to light. That's what a photoconductive material is. So, what you have here, this is the xerographic or Xerox process. And of course, Xerox is the company that came out with it. It's almost such old technology now that people use aspects of it, but they don't quite use all the same thing. So here we have a drum that's coated with selenium, which tends to attract positive charges. And you charge that drum with the positive charges. Okay? Now, your document is up here. You shine a bright light on that document. Okay? The white, the light gets through. The dark, the O here, the light doesn't get through. You send that through a lens which focuses that light. And now, because this is a photoconductive material, the dark parts stay the positive charge, the light part conducts it away. Where the light comes through, that conducts away, so you're left with positive charge there. Okay? Lots of positive charge. You have negatively charged toner. Okay? That coats those positive charges. Okay? and then your next piece of paper comes in, and the paper is slightly positively charged. This is negatively charged there. The negative charge toner then affixes itself, attracts itself to the paper, and then what you do is heat it and fix it in place. Okay? Now, that's how we used to do it optically, the xerographic process. Later they came out with, I think HP came out with this, the laser printer that does a similar type thing, but rather than just photoconductive, it actually is a very specific laser beam here, and that's even sharper and not as charged, okay, I don't think, as the old Xerox was. The text does a lot better description of it than what than the slide does here. Okay.
Laser's faster. Isn't it?
What's that?
Laser's faster.
Laser faxes? Is that what you said? I think so. I think it is. And the main reason is this is light, which is all the things, whereas laser is basically one wavelength. That's what makes a laser. Also what makes it pretty tough on your eyes. Don't ever get your shine a laser light into someone's eye because you can do a lot of damage there. But it is much more, I want to say specific. That's not quite the word I'm looking for. But I think sharper might be a good analogy. Okay. So here's the application of a laser printer as opposed to a Xerox, which is white. Okay. The steps for producing a lot of document on a laser printer, very similar to xerographic, which is just light. Steps A, C, and D are the same. The major difference is the way that the image forms from the selenium-coated drum. Still the same drum with positive charges on it. The rotating mirror inside the printer causes the beam of the laser to sweep across the selenium-coated drum. And that's why they indicated this. You have the sweeping that goes on here, okay? Whereas here, it was just the focus down, and the drum picked it all up at once. Here, the laser beam is sweeping across it constantly, okay? Now, the electrical signals form the desired letter in the positive charges on the selenium-coated drum. The toner is applied, and the process continues just like xerographic, okay? Except that you have the laser, which I think is just so much sharper than the light, which can have some diffraction, fuzziness to it, okay? That was just an application. Again, your book does a lot better description than I can do just talking about the slide. So please read the text. Okay? Now we're moving to the area of capacitance. Okay? Now, voltages, capacitances. Very different things, but they are in many ways somewhat related. What a capacitor is what we've actually been talking about for a couple of chapters, those parallel plates, one positive, one negative. Capacitor is a device used in a variety of electric circuits. The capacitance, C. Now, I apologize for this ahead of time, but please don't get them confused. When we're talking about capacitance and give it the capital C, that is a parameter, that is a feature, that is a characteristic. If you had a number in front of there, you're talking about so many coulombs. Capital C coulomb is a unit following a number, capital C by itself is capacitance, which is a feature or property, a parameter of the system. So the capacitance C of a capacitor is defined as the ratio of the magnitude of charge on either conductor or plate, these are usually parallel plates, to the magnitude of the potential difference between the conductors. So you see what capacitance is? It's charge per unit per potential difference. So a capacitance would be, okay, coulombs per volt. That's what capacitance is, coulombs per volt, okay? And again, don't get these confused. Charge, the symbol for charge is Q, right? The unit for charge is coulomb, capital C. Capacitance, the symbol is capital C, the units are coulombs per volt, okay? So don't get those crossed up there. Maybe my mentioning it is going to make them more easily crossed up. But anyway, here's what we've got. You define capacitance as charge per potential difference. Coulombs per volt. Okay, the capacitance is measured in farads. Okay, charge is measured in coulombs, which is capital C. Capacitance is measured in farads, which is capital F. Now, why would it be a capital F?
Because it was named after somebody.
And who would that be?
Faraday.
Faraday, exactly. Farad is the first 5 letters in Faraday. Okay? So in units, 1 farad is 1 coulomb per volt. Okay? Now, most of the time we deal with capacitances. A farad is an extraordinarily large number. We seldom will have a farad of capacitance. We often see microfarads or picofarads, okay? That's 10 to the minus 6, 10 to the minus 9, maybe? No, 10 to the minus 12. Yeah, 10 to the minus 12. What is 10 to the minus 9? Goodness, I forgot my unit. Well, my word. It's early in the first chapter. Ha! I just found something I was looking for. A week ago. I lost it. I called them and got it, but there it is again. Okay. I knew it was somewhere here. Okay, here we go. Nano, of course, I knew that. In between micro and pico is nano. So you will see microfarads, nanofarads, or picofarads. 10 to the minus 9 is nano. Now, delta V, voltage, potential difference across a conductor. That could be in units, tens, hundreds, thousands, kilovolts. Usually you don't get any bigger than that. Or it could be small, millivolts or things like that. Seldom anything as small as this. So V represents the actual potential difference due to a given charge at a given location. Okay? Now, how much charge? Usually the charge numbers are very small. That's what drives the capacitance to be very small numbers. Voltages can be any range of numbers. Okay? Can't be quite big, which again would drive the capacitance to be very, very small. Okay. So let's look at the good old standard parallel plate capacitor. We've actually looked at that in several other instances. It says it's an example. It really doesn't give an example with it. But this picture is in your book on page 541. The capacitor consists of two parallel plates. Each has the same area A, both plates. They're separated by a distance D, and that can be a very small separation too, typically is. In fact, always very small in number compared to the area. That's a given. The plates carry equal but opposite charges. One is plus Q, one is minus Q. Not plus 2Q and minus 3Q. They have to be the same. Okay. When connected to the battery, the charge is pulled off one plate and sent to the other plate. Okay? Which one is that? In reality, it's the electrons pulled off the positive plates and sent to the negative plates. You don't move protons around. You move electrons. But you could think of the charges, the positive charge being pulled off the negative plate and moved to the positive plate. Just think of it that way. It's just that usually it's electrons that are actually being moved. Okay? The transfer stops when the delta V of the capacitor is equal to the delta V of the battery. It takes a while for it to happen. Usually it's a fairly short time constant. Usually. Plates carry equal and opposite charges. Okay? Keep this in mind when you're dealing with capacitors. The charges of the two plates have to be the same, and the voltage across it has to be your voltage drop of whatever your circuit element is there. Okay. So, the capacitance of a device depends on the geometric arrangement of the conductors. They don't have to be parallel plate capacitors. They could be other. But for a parallel plate capacitor, whose plates are separated by air, then the capacitance is some epsilon zero, and this is called the permittivity of free space, times its area divided by the D. Okay? You remember the area is quite large compared to a small distance in between, but this is an extraordinarily small number, epsilon naught. Okay? Now, they did a bit of work to get from the previous definition of capacitance to this one, and it's well worth your read to follow that. It can be a tad on the confusing side, okay? But hang with it and you'll see that things start canceling and you get this. Now, the epsilon zero is the permittivity of free space. And again, physical constants are in the back of your book. The permittivity of free space, epsilon naught, is 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. Okay? So again, that's an extraordinarily small number. Okay? Now this is for parallel plate capacitors. So you see this is an extraordinarily tiny number. Usually A is significantly larger than D, but nowhere close to being as small as this number is. Okay? So now, as you might think, and hopefully you will be thinking this, the larger the area is, the more charge you can store, so that the capacitance goes up. Okay? Strangely enough, the smaller the distance is, that also goes up. But you can't get too small here because you tend to discharge if you get too small there. So, especially if you have a large potential difference. Okay. Now, I think your first lab, you hit this concept. We talked about it back then. We didn't call them capacitors, we just called them parallel plates. One positive, one negative. Okay? And we talked about electric field. So all this stuff is, it was the second lab, the lab we did last time. You had something very similar to this. You talked about it, you didn't have to draw it. Basically what you drew was something in here. You just let these go on out. Notice in a parallel plate capacitor, the field lines near the center are basically uniform. Okay? In other words, that's the closest you ever get to having a uniform electric field in the middle of a parallel plate capacitor. The electric field between the plates is uniform near the center, but non-uniform near the edges. Because you see out here, you get the field lines can go like this and actually leave and go around like that. So you don't have uniform field lines here, only near the center. I don't like this slide because they should have uniform here and non-uniform there. You know, they shouldn't have uniform there, and then this one isn't parallel with that. Okay. The field may be taken as constant throughout the region between the plates. It really isn't near the edges, but we usually don't live near the edges. In between, you take that field as being pretty constant. Okay? And that would be in newtons per coulomb or volts per meter. Either one of those that you want to use.
It's time to take roll again.
It's what?
It's time to take roll again.
Oh, is it? Thank you. Let's see. I have to go back. We started at 5:30. Yeah, you're right. Well, technically, we really should be having a little break now, but if you want to keep trucking, maybe we can leave a little early. Okay. Tia's here. Megan's here.
Do you have those,
I'm sorry.
the first lab in the test?
The first lab and test? Oh, yeah, I can get those to you. Let me go on and mark the roll first here. Aoife did not make it back. She was here earlier, but not now. Okay, great. Okay, Tia's here, Megan's here, Sakina's here. We haven't seen Charity, even though she added. Haven't seen T at all. Courtney's still here. Sam's still here. Brianna's still here. And we haven't seen Kamari at all. Okay? He's a Lawson student that pre-registered but never has shown, so I guess he's not coming this summer. No. As far as I know, he hasn't. I haven't looked lately, but last time I checked, he still hadn't. But they're keeping his name on the roll, so I can't do anything with him until they take him off. I saw the registrar not long ago, I think it was last Wednesday or Thursday, and said, she was asking me about no-shows, which are paid students who haven't come. I said, well, I don't have many of those, but how about the non-paid student? Oh, are they still on there? I said, yeah, they're still on there, so what are you, oh, okay, well, we'll talk about getting those off. I have to talk with the vice president, so I don't know if she's gotten in touch with them or not. It may be the next time I check it, they'll be gone. Okay, yeah, I was just waiting to see. Yeah, this is a great place for a bladder break. Okay.
Hey, did you teach at,
What's that?
did you teach at Abrams High School?
At where?
A high school?
No,
Oh, you did?
I'm a full-time instructor here.
Like, back in the day.
Oh, no, I've never. I have taught a couple of high schools, but not on a full-time basis. I was a substitute teacher or a replacement teacher, but only for a couple months. Yeah, but no, I've never been a full-time instructor or teacher at a high school. All right, I'm going to put this on hold for now. Okay. All right, we are recording again. I was just waiting for the projection to catch up. Let's look at some applications of capacitors. There's actually a big application in the room right now. The lights, yeah. Fluorescent lights have to have a pretty large potential difference to get that stream of electrons to move up and down the tubes, okay? That's done by, I don't know if you've ever been inside or looked inside this, they have a big box they call a, they have a name for it, ballast. And the ballast is a big capacitor, which builds up a lot of charge, and then that's what discharges up and down. It's a continual type thing for that. A camera flash, on the other hand, that's the one they're doing here, is a very rapid discharge. The flash attachment on a camera uses a capacitor. The battery is used to charge that capacitor, and that can be at a fairly slow rate and stuff like this. The energy stored in the capacitor is released when the button is pressed and pushed to take a picture, and then suddenly you get the bright flash. The charge is delivered very quickly, illuminating the subject when more light is needed, and that's exactly how a camera flash works, okay? Now, the old days, remember, it was gunpowder in a tray, you know, if you've ever seen the movies of that, that actually something burned, and it may not have been gunpowder, it was something that burned very brightly. But a capacitor does it without the fire, and it does do. Now, in the old days of camera, you could only use the flash bulb once, because literally you blew the bulb when you used it. Nowadays, it's a capacitor that can be reused time and time and time again, okay? So that's one application of a capacitor. Very large amount of charge builds up, and then you discharge it very quickly, giving off a flash of light. Here's something that several of you are using right now, okay? Now, especially on computers or on any keyboard, computers or any keyboard, electronic keyboard, use the capacitors in many ways. Some keyboards use capacitors at the bases of the keys. So when you have, say, a B key there, when you press it, now we're getting into something we haven't hit yet, dielectric. We're going to get to that in a minute. Have the fixed plate and the movable plate. And when you press the key, you push the plate down, compressing the dielectric, okay? And we haven't talked about that dielectric yet, but we're going to get to it soon. When the key is pressed, the capacitor spacing decreases, the capacitance increases, and the key is recognized by a change of capacitance. So basically, when you're typing along on your screen, whatever you're using, and you're typing along, every time you press it, you're sending a capacitance signal, and that translates, that capacitance from that one translates to be a beat. Okay? You don't actually have a key that goes up like the old typewriters did, or a ball that turns and presses into it. You're actually sending an electronic signal that corresponds to the letter B or whichever letter you happen to hit. Okay? Another application. Now this is electrostatic confinement, which is something you don't run into all the time, but this is used in fusion research. Now, again, what is fusion? I think we talked about it in this class. I have in some of my other classes. That is the combination of two nuclei to make a new thing. A hydrogen bomb is a fusion bomb. What's going on the sun right now? Fusion. Hydrogen is fusing to helium. What's going on some bigger stars that are in the process of burning themselves out? You can have helium fusing to carbon, carbon fusing to other heavier elements up to iron. When you do fusion research, you're trying to do that on a very, very small controlled scale. So you need to build up an awful lot of energy, think charge, in a very small space to try to make fusion happen. The capacitors discharge their electrons through a grid. The electrons draw positively charged particles to them. Some particles will fuse and release energy in the process, as in two protons coming closer together, fusing and become helium, giving off an awful lot of energy. But you're trying to do that on an atomic scale, so that awful lot of energy is really not that much, but if you have enough of it going on, then you can. This is what they call controlled fusion, or cold fusion, they sometimes call it. You don't need the enormous energy or heat to make it happen as a hydrogen bomb would. You don't want that happening, okay? Now, let's think about capacitors in circuits, okay? A circuit is a collection of objects usually containing a source of electrical energy. That could be a battery, a power supply. It could be alternating current, so it could be your plug in the wall. Connected to elements that convert electrical energy into other forms. Okay? For instance, a resistor basically converts electrical energy to heat. A capacitor converts electrical energy. Well, we'll get there later. Let's just hang with it. Circuit diagram can be used to show the path of the real circuit, or at least a replica of that path. Okay? Now, we're going to do this in later chapters. In fact, a lot of times you will have already done this for resistors. This book does capacitors first, and it's fine. There's no reason not to. But people aren't as used to capacitors. But when you have capacitors in parallel, that means here's your battery down here. This is your total voltage difference. Okay, you have two capacitors up here. One parallel plate here and one parallel plate there. Now, usually they're given symbols and you don't have to actually draw the plate. We'll get to that in a minute. Okay? Now, because these are in parallel with each other, the same potential differences across each of these. Okay? However, if you think about the formula, the equation that represents this, remember C, let's do C1, is equal to the ratio of Q to delta V. Remember that? That's how we define capacitance. Okay? So, the delta V being the same, this would have a different charge. If C1 was different from C2, you'd have a different charge. Now, each plate in the parallel thing has the same charge with opposite sign. But these two plates don't have to have the same because the capacitance is different. So this could have, if this C1, let's say it's less than C2, okay? Then because C1 is the ratio of Q1 to delta V, and C2 is the ratio of Q2 to delta V, and C1 was less than C2, that means the Q1 would be less than Q2. So you would have more charge across this capacitor and less charge across that. Same charge on both plates for that one, but the charge would be different. What does that mean? This battery has to be supplying enough charge to do this one and that one. So in other words, the amount of charge on these two capacitors, the sum of that has to be the charge coming out of the battery. Okay? So when connected in parallel, both have the same potential difference across, but they typically would not have the same charges unless they were identical capacitors. Okay? And when we do the lab for this chapter, which will be the last 2 hours of next class, that'll be on Monday, we will play around with this some. Okay? So, capacitors in parallel, when capacitors are first connected in the circuit, the electrons are transferred, let's go back to this. Remember, it's electrons that are moved, are transferred from the left plates to the right plates. Because electrons are really moving the circuit. You don't move protons around, you move electrons. So you move the negative charges off of this plate, leaving it positive, off of this plate, leaving it positive, and the battery pumps them over here, making this more negative. Same charge on both plates, this is positive, that's negative, same magnitude of charge, but because the capacitors are different, then you would have different amounts of charge on the two different capacitors. Okay? So that's why they said from the left plate to the right plate. You couldn't see that, so I went back there. Leaving the left plate positive charge, the right plate negative charge. The flow of charges ceases when the voltage across the capacitors equals that of the battery. Got to. The capacitors reach the maximum charge when the flow of charge ceases. And because they have different capacitors, they may be different charges. Okay, just assuming, because they named them different, C1 and C2, assuming those are different. Now this is the representation. You don't have to draw the plates in 3 dimensions. Here's how you represent a capacitor. 2 parallel plates, 2 parallel lines. That's how you do it. Now that looks a lot like a voltage source, a battery. Here's the difference. A battery always has a large and a small. Large being positive, small being negative. Does that mean the plates in the batteries are different sizes? No. It's the convention that you put the plus on the large side of the battery and the minus on the small side of the battery. That lets you know where your potential difference is. Your parallel plate capacitors, you put the 2 parallel lines equal to each other because they're supposed to be equal area, equal charges, everything equal. These are not equal, one's positive, one negative. Well, these are not equal, but you still place them that way. That's how you distinguish a battery from a capacitor. Capacitor, the plates are the parallel lines are the same size. A battery, the plus is larger than the negative. Okay? The total charge Q is equal to the sum of the charges on the capacitors. Okay? So the total charge being sent by the battery, moved by the battery, is the charge here, Q1, plus the charge here, Q2. Again, the voltage difference is the same across both of those, so all that matters is the capacitors is they're different, the Qs are different by the same ratio. Okay? So the total charge Q is equal that the battery is having to pump is equal to this Q1 plus Q2. Make sense? Okay. Now, you could then talk about an equivalent capacitor that would just be the sum of those other 2 capacitors. Because you could even think of it this way, the areas are added, the charges are added, so you could just think the equivalent capacitance would be the sum of those 2 capacitors. Okay, the capacitors could be replaced with one capacitor of capacitor QEQ, which means equivalent capacitance. The equivalent capacitor must have exactly the same external effect on the circuit as the original capacitors, which would be moving Q1 plus Q2 charge, which of course this would be the same. Okay? You'd have Q plus Q1 positive here, Q plus Q2 negative there. You would have, that's exactly the same. So, in a parallel circuit, the capacitances add. Later when we do resistors, completely the opposite. Okay? But a parallel circuit, the capacitances add. So if you had a string of capacitors all in parallel, then you just add them all up. C1 plus C2 plus C3, as many as you have, that would be your equivalent capacitors. The equivalent capacitance of a parallel combination of capacitors is greater than the individual capacitances. It's got to be, because you're adding them up. These are just numbers you're adding up. So the equivalent has got to be greater than the greatest of the individual capacitors when they're parallel. Remember that, when they're parallel. Okay? What if you had your capacitors in series? Okay? And that means on the positive side here, you're connecting to the positive side of this capacitance. And then this has to have exactly the same charge here as negative. But this is connected here So these have to be the same, and these are connected here, and those have to be the same. So when you have capacitances in series, okay, think of it this way. The battery is pumping the charges off of this, the electrons off of this one, and moving them to here. When that happens, then this is drawing positive charges here. In other words, the negative charges are moving from here to here. And guess what? All the charges have to be the same, even if the capacitors are different. The charges have to be the same in a series circuit. Okay? But if the capacitances are different, that means you have a different voltage drop across this one than you have across this one. But that makes sense because your voltage drop here has to be the sum of the voltage drop here and the voltage drop here. So, on series capacitors, your charges are equal. Even if the capacitances are different, because the charges are equal, the capacitors are different, that means a different voltage drop across each one. And these two voltage drops add to be the voltage drop across the battery. Okay? So the magnitude of the charge must be the same on every plate in that series circuit. Every plate. If you have 3 or 4 of them there, the charges have to be identical on every plate, even if the capacitances are different. That makes a different voltage drop across each one. And those voltage drops add to be the voltage drop across your battery. Does that make sense? Okay? So, capacitors in series, when a battery is connected to the circuit, the electrons are transferred from the left plate of C1 to the right plate of C2. I sort of wave my arms on that one. Okay? As that negative charge accumulates on the right plate of C2, an equivalent amount of negative charge is removed from the left plate of C2, moving to the right plate of C1, okay, because those two have to be the same, these two have to be the same, these two are the same, that means those two are the same, and everything's the same. So all the right plates have gain charges of minus Q, all the left plates have charges of plus 2, so all the plates have the same amount of charge, signs are vary, the same amount of charge, but different capacitances, which means a different voltage drop across each capacitor. Okay? Now, what's your equivalent capacitance then? The equivalent capacitor then would be the two potential differences have to add to be this across the battery, and those two potential differences add I wish they had said something about the charges here. That would make it all a lot clearer. But if those two voltages have to be the same, maybe they will say it in the next slide. It's just, yeah. Let's go back to this. Okay, remember, C1 has to be Q over V1, delta V1. Has to be, that's the definition of it. C2 has to be the same Q over the delta V2, okay? But these delta V's are different if those C's are different, because the Q's have to be the same. That's why I said I wish they had shown the charges on that next slide too. So the two delta V's have to add, okay, to make this. The Q's are the same, okay? But because of the relationship between that, it's Q over delta V, okay? So the C's correspond to the Q's there, and I just hate that they don't do a better job of explaining. But because the delta V has to be the same, and here, it just bugs me they don't do this. Okay. C1 is equal to Q over delta V1. C2 is equal to the same Q over delta V2. Okay? Now, rearrange this and make this delta V1 is equal to Q over C1. Delta V2 is equal to Q over C2. The Q's are all the same. The Q's are all the same. So that means your 1 over C1 plus 1 over C2, you just are taking out the Q here, that's the same as 1 over the equivalent capacitance. You could put the Q's in there, then divide them off. I wish they had done that, but they didn't. They just put 1s up there because all those Q's are exactly the same. Okay, well, what does that mean? Okay, if you think about this, when you have a big number here, that's now a smaller fraction, right? A big number here makes this a smaller fraction. If you add these two fractions together, you're going to get, a little bit larger fraction, but then this thing has to be less than either of those two. So the unusual thing is the equivalent capacitance of a series is always less than the individual capacitor in the combination. The least of the individual capacitors in the combination. So it's a reciprocal relationship. You add more capacitors in series, you drop the capacitance of the effective capacitance of the system. It seems bizarre. Put more capacitors in there, your overall equivalent capacitance decreases. It doesn't increase. Whereas in parallel, they increase big time. And you'll find that's true of all the things. If one goes one way, the other has to go the other way. Okay? So, problem-solving strategy. A very important thing to put in any problem-solving, and they didn't do this in all of them. And by the way, your text has several examples, and I'll be glad to do any of those if you really need to see those. These are not, what would you say, they'll always follow what you would expect. So you may have some surprises here. But there is a quick quiz at the bottom of page 547. Okay? A capacitor is designed so that one plate is large and the other is small. Typically, that's not how they do. If the plates are connected to a battery, A, the large plate has a greater charge than the small plate. True or false? Okay, capacitor design, one plate is large, the other is small. Connected to the battery, does the large plate have a greater charge than the small plate? No, because charge is conserved. If you move charge off of this one, it deposits here. So the charge has still got to be the same. So A is not true. The large plate has less charge than the small plate. No, because if the charge is moved off of one, it's moved on to the other, so the charge is the same. The plates have equal but opposite charge. Yes. Got to be. So quick quiz 16.8 had better be C, equal but opposite charges, even if the plate size is different. Now what differs is the charge density on the plate, the charge per unit area. That would definitely be different. So here's our problem-solving strategy. If y'all don't want to see some of these, I'll be glad to do any of them if you do. They're pretty straightforward, but just pay attention to them. Capacitor, complex capacitor combinations. Problem-solving strategy. First thing it says, be careful with the choice of units. Okay? Now this is not exactly how it's stated in your text, but I think it's a very important thing to stay first. Be careful with your choice of units. Okay? Okay, get that done. Now, combine capacitors following the formulas. Okay? This is where they start in the book on number 1. When 2 or more unequal capacitors are connected in series, they have to carry the same charge. Have to carry the same charge if they're in series. But the potential differences across them are not the same because they add up to be the total potential difference of the battery. The capacitances add as reciprocals, and their equivalent capacitance is always, always, always less than the smallest of the individual capacitors. Gotta be. Okay? Next, when 2 or more capacitors are connected in parallel, the potential difference across them are the same, so the charge on each capacitor is proportional to the capacitance. Larger capacitance up here, smaller here, more charge here, less charge there. But the potential difference is the same. The capacitors then add directly to give the equivalent capacitance. So the parallel circuits, they add just like you would expect them to. Small capacitance, large capacitor, add them together, that's the total capacitance larger than either of the other two. When they're in series, small capacitance, large capacitance, effective capacitance less than the least of these. Okay? Always. Okay? Now, again, what they're talking about here are complex systems, not just simple parallel or simple series, but combinations of some parallel, some series, in various combinations. So every time you come up with an equivalent circuit, equivalent capacitance, redraw it with that one in there. That's what they're meaning redraw. Repeat the process until there's only one single equivalent capacitor. The complicated circuit can often be reduced to a single equivalent capacitor. Replace the capacitors in series or parallel with the equivalent, and then redraw the circuit and continue. And just keep on until you get it down to 1. To find the charge on or the potential difference across one of the capacitors, start with your final equivalent capacitor and work back through the circuit reductions. Now, this is a lot of blah, blah, blah now. I think the only way you actually will see this is to do this. Okay? Let's see if they'll give us an example. Well, they're still talking this. Okay? Use the following equations when working through the circuit diagrams. Okay? Remember, your capacitance is always your charge per unit voltage difference. If you have capacitors in series, add them up. In parallel, add them up. Capacitors in parallel all have the same voltage difference across them as of their equivalent capacitors. Capacitors in series, on the other hand, add as reciprocals, and then the equivalent is the reciprocal of those additions of reciprocals. Okay? Capacitors in series all have the same charge, Q, as does their equivalent capacitors, but, and that's the thing they didn't show before, I wish they had, they're saying it now, but their voltages, which are related to that, are different, and they add to the total voltage. All right, here we go. Here is a complex, not that bad, but a complex situation. Now, the numbers here refer to capacitances, okay? And notice here they didn't give you a voltage across it. You don't really need it. You just need to know that there is a voltage across there, okay? Now, here we have, starting with A, you have a single capacitor here for, in series with 2 parallel capacitors, 1 and 3. And down here, this is in parallel with a parallel capacitor 6 and 2 in series with an 8 before you get to B. So what you do is go to the smallest similar unit that you got. This one. These are in parallel or series. Parallel. What happens to your capacitors in a parallel system? They add together. So you add 1 and 3 and you get a 4 right there. Okay? Look at this system. Let's see. The next one here, what do these do? What kind of system is that? Parallel or series? Parallel. What happens to your capacitors? They add, so that gives you an 8. And that's now in series with the 8. So this 4 is in series with the 4. So we redraw it. Every time you take care of one element that's the same, redraw it into this. So now you have these two in what? Parallel or series? Series. So what happens to your capacitance here? They don't subtract. They add by the inverses. So this would be 1 over 4 plus 1 over 4. What's 1 over 4 plus 1 over 4? 2 over 4, which is 1 over 2. So your equivalent capacitance here would be 2. 1 over C2. So this equivalent is just a 2. Okay? This is these are in series. So what do you do with your capacitances? Add reciprocals. 1 over 8 plus 1 over 8 gives you, okay?
No.
2 over 8, which is 1 over 4. So the equivalent would be 4. You take the reciprocal of it, 4. So that gives you a 4. Well, what are these two now? Parallel. Okay, and what you do with capacitance, you add them together. 2 plus 4 is 6. So the overall is 6. This whole complicated looking thing gives you an equivalent capacitance of 6. Okay? Now, if you knew the voltage there, you see you didn't need the voltages anywhere here. If you knew the voltage there and you knew the capacitance here, 6, you could calculate the charge on each of these plates. Right? Okay. So if you know the voltage here, that's the same as the voltage here. And the same voltage across here is here, so you could get the charge on this one and the charge on this one, because if you knew that voltage, then using the formula, C is equal to, Q is equal to C delta V. That's the one I like to use because it's multiplied. But C is equal to Q over delta V, multiply both sides by delta V, and you get Q is equal to C delta V. Okay? If you know the voltage, you know the capacitance, you can get the charge here. Okay? Well, these here, you can get the charge here and the charge here. These two charges have to be adding to get the same charges there, because this is parallel. So you got that one back. Then you get to this system. So you work your way back, and once you know the charge here, that same charge has to be on all these plates, and the same charge there has to be on all those plates, and then you have a different delta V. So you just keep working backward until you get the charges, the voltage drops, and everything across every part of your system, and you got it on. You have the whole system totally defined. We will be doing this in the next lab. This will be the lab we do on Monday. The last 2 hours Monday. We'll actually just sit down and take some simple measurements, and then we'll do all our calculations somewhat similar to this. Okay? And we'll do simply, and then we'll combine again. So, what's that? Okay. Now, this problem that you see here is example 16.9 in the text. And it says solve the complex combination of series and parallel capacitors. Okay? And what you're asked to do is calculate the equivalent capacitance between A and B for that whole thing. We did that. We did it and came up with 6. So that's done. Okay? All capacitances are measured in microfarads. So these are all microfarads, every one of those. Now B, this is where we say if a 12-volt battery is connected across the system between A and B. That's between every A and B. Find the charge on the 4 microfarad capacitor, that one right there. We have to find that one, the charge on that in the first diagram, and the voltage drop across. So what we're looking for is Q here and delta V here. Can you get from there to there and do it? Not in one step. So what you have to do, let's do it. You know that your delta V here is equal to 12 volts. Okay? Your capacitance here is 6.0 microfarads. Okay? And like I said before, your Q is equal to C delta V. Okay? Now, so the Q here would be 6 times 12, which would be 72 microcoulombs. Okay? Because this was in volts and that was in microfarads, this will be in microcoulombs. Just multiply this times that. Okay? 72 microcoulombs. That's how much charge is on each plate. Okay? Now, we also know, I'm going to do them all. We don't have to. All we really have to do is this one, to get this one, to get this one, to get that. Okay? I'm going to do both of them just to see how they pan out. Okay? Now, your delta V across here and here are the same. So let's do the same thing we just did. The Q here is 2.0 microfarads times 12 volts, because you see this is still 12 volts across there, so this is 24 microcoulombs. Okay? Down here it would be 4 times 12, which would be 48 microcoulombs. And guess what? You add those two together, right? And you get 72. I sure hope so. Yeah, you do. 72 microcoulombs. 24 plus 48 is 72 microcoulombs. Okay? So we got that. Let's go back another step. Okay? This is what you got across this capacitor here. Equivalent capacitor to these two. This is in series. And in series, the same charge across this is across both of those. Because this is how much charge you have here and here, here and here, here and here. Everything's the same. So you know that the charge here for each of these is 24 microcoulombs. This is 24 microcoulombs. This down here is 48 microcoulombs. This is 48 microcoulombs. Because they're in series, and in series the charge stays the same, and it's the same as the equivalent. Follow it? Okay? Now, what we wanted to know, remind ourselves what we're looking for, we want to know the charge across the 4 microfarad over here. So we are looking for charge, so we got charges so far. Also the voltage drop across. So you have to keep up with your voltage drops as well. Okay? Well, you know the total voltage drop across these two is 12, and across these two is 12. But these add. So you have a different voltage drop across this one as you do across that one. And basically, time out, if you know you got 24 microcoulombs across here, that's the same as here. So you already have that answer. What's the charge across this one? The 4 microfarad is 24 microcoulombs. From right here, you know that's the case. Okay? The second thing it asks is the voltage drop across this one. Well, that's what we're about to do now. Well, same formula you used here. Q is equal to C delta V. Now solve for delta V. Delta V is Q divided by C. Delta V is equal to Q divided by C. Well, you know the charge across here is 24 microcoulombs, and the capacitor there is 4 microfarads. Well, guess what? That's 6.0 volts. So 6 volts across there. And 6 volts across here, 6 and 6 adds to be 12. If you did the same thing here and did 48 divided by 8, 6 and 6 adds to be 12, okay? Now, the only thing we haven't done is how these break down. But you do that the same way as we did before. You know, this is 24 microcoulombs across each of those with the same voltage across there. We know that's 6 volts across here, and that's 1 microfarad. So go back here, and you have the charge across that one would be then 6 microcoulombs. The charge across this one would be 18 microcoulombs. Add those together, 6 and 18 would be 24 plus 24 is 48. Yes, yes, yes. You know the voltage drop, the charge, and the capacitance of every one of those. You dealt with the capacitances first. That was pretty easy. Then you went backwards and calculated the delta V's and the C's. No, delta V's and the charges. Okay. So we came up with 24, and we came up with, what do we say, 6 volts. Look at the answer in the back, in the book, 24 microcoulombs, 6.0 volts. Done. Okay. They really work out pretty nicely. Okay. Now, 16.7 is energy stored in a capacitor. Okay? They give you the formula here. Energy stored is 1/2 Q times delta V. Now, where did they get that? Okay? If you remember the definition of delta V, that's energy per charge, right? That's how we define that. So multiplying that by the charge, that gives you energy, except you have a 1/2 there. Now, where did the 1/2 come from?
That's just the formula.
What's that?
That's just the formula.
It's just, yeah, it is just a formula. So your units are right. That's what telling you your units are right. Basically, what you can think of as giving you that, remember the same charge is on each plate. So you can think of it as in the average charge would be half of on for the whole thing. But actually, let's see if they have this slide. No, they don't. In your book, you'll see the delta V here versus the Q here, and the total energy of each thing would be delta V times delta Q, but it's a line that goes like this. The total area is 1/2 the base times the height, because you're forming that triangle. As you go up and delta V this way, Q this way. When you have no voltage, you have no current. I mean, no charge. When you increase the voltage, you increase the charge. You increase the voltage, you increase the charge. Well, the total energy is the area under here, which is 1/2 the base, which is your Q, times your average height, which is your delta V. So that's really where it comes from, is the fact that you're doing an area of a triangle rather than an area of a square. Okay. Now, so that's the amount of energy stored. Okay. I want to introduce a couple of other things. Remember this, C is equal to Q over delta V, right? Okay. Now, so what you can do is solve this and say Q is equal to C delta V. Like I told you, that's my favorite of the formulas. It's easier for me to remember. So instead of Q, put in that. So the energy stored is equal to 1/2. Instead of Q, put C delta V, and then multiply it by delta V, you get delta V squared. Okay? And that gives you this formula right here. 1/2 C delta V squared. That's equivalent to that. Okay? Now, the other thing you can do is solve that for delta V. Delta V is equal to Q over C. So here we have 1/2 Q times Q over C. Well, this is 1/2 Q squared over C, which is the same as Q squared over 2C. So that's how you get the third one. So by just using the formula and do it, this is energy in terms of charge and voltage. This is energy in terms of capacitance and voltage. This is energy in terms of charge and capacitance. Now, why they put the 1/2 out for these two and put the 2 there, it doesn't matter. I like to say, if you're going to do it these two this way, do 1/2 Q squared over C. You know, that's how I wrote it, and it works out just as well. Okay? So 3 different equations for the energy stored in the capacitor. And it all comes from your original one, whichever you want to remember first, and then the fact that Q is equal to C delta V, or solve that for delta V is equal to Q over C. Whichever you're solving for, plug it in for the other, and you can get all 3. Okay. And the book does it the same way. They put the 2 down here, but they put 1/2 in front over there. I do not know why. There's no real reason to. And that, by the way, when you say energy, this is always potential energy. Okay? There is no kinetic to do with that, and that's called the potential energy of a capacitor. Okay? Now, here's an application of that. Defibrillators. Have y'all, I know you've seen ER or some show like this, and they say, stand back, charge, you know, and they start somebody's heartbeat again. Okay? That's called a defibrillator. When a fibrillation occurs, that means the heart is producing a rapid, irregular pattern of beats, is not being very efficient in pumping blood. And that could lead to a heart attack or a stroke or lots of real big problems, like not enough blood getting to the brain or some other organ, and you go into rapid decline and could lead to death. Okay, a fast discharge of electrical energy through the heart can return the organ to its normal beat pattern. So that's why they put it on one side or the other and then hit it, you know. But everybody stands back because it's a fairly large amount of electrical energy going through there. In general, capacitors act as energy reserves, or reservoirs, that can be slowly charged, then discharged very quickly to provide that large amount of energy in a short pulse. That's what your flash bulb does. You have slowly charge it up, and then when you want to discharge, a large amount comes around right at once. It can be released more slowly, like the keys on your computer, okay, my computer or whatever, okay, or slowly released, but continually being released through the thing. You just need a large amount of charge in those tubes, more than you'll get just out of the circuit, so your capacitor stores that for you, and therefore you can discharge large amounts. Okay? So there's an application, and the defibrillator discharges a large amount in a very short time, but it charges slowly. Now, as I mentioned before, there's this issue with dielectrics, and we saw them in the computer keys. I said, wait, we'll get there. Here we're there. Okay? A dielectric, okay, is an insulating material. Why would you put an insulator there? When placed between the plates of the capacitor, increases the capacitor more than just air alone. Normally, you just have air between them. If you put a dielectric in there, you actually have a greater capacitor for the same size. Dielectrics include rubber, a good insulator, plastic, a good insulator, wax paper, a good insulator. Okay? I don't know what the material is under the keys, but it's something that can be maybe a foam or something like that. You just are able to press it or not. Okay? Now, here's the formula. Your new capacitance is equal to, now this looks like a K, that's a kappa. The Greek letter K, capital K, that's a kappa times C0. This would be the capacitor if it was only air in between there. When you have the dielectric in there, this is called the dielectric constant. Okay? Now remember what this C0 was? It was your epsilon naught, the permittivity of free space, times A divided by D. A being the area of the plate, and D being the space between, and that gives you the C0, multiply that by K, and that gives you the capacitance. The capacitance is multiplied by the factor kappa, I say K is kappa, when the dielectric completely fills the region between the plates. Kappa is called the dielectric constant. Okay? Now, I know they have a table in the book. Let's see if we can. Okay, first let's see a picture of it. Now, what you do is you have some potential difference, let's say in 2 volts, across these parallel plate capacitors. The capacitance is C0. Okay, you calculate and see what it is. That gives you C0. That gives you some charge of Q0. Okay. Now, you put a dielectric in between that. That's a chunk of plastic, let's say, or rubber or something in between those 2 plates. And now, for this, okay, they're changing too many things. For the same charge to build up here and here, you only need half the voltage, because the delta V 0 here, 2, divided by kappa, in this case would be 2, that's your new potential difference of 1. So basically this is showing a capacitance, a dielectric constant of 2. Your capacitance is now 2 times your original capacitance. Whatever that C0 was, you've now doubled it. Same space, same size plate, same everything. You drop the amount of voltage, increase the capacitance. Okay? Now, what do we mean by that dielectric strength? For any given plate separation, there is a maximum electric field that can be produced in the dielectric before it breaks down and begins to conduct. Remember, the concept here, it has to be a non-conductor, okay? But if you put too big a potential difference across there, it's going to conduct. think this. I was in Louisiana over the weekend, so I mean, first part of the week, they had some pretty massive thunderstorms there. Do we have any here? No. I think we maybe gonna get those tonight. But think about what's happened there. You have these clouds, and they rub against each other, bump against each other. They exchange charges, and you get a big potential difference between the two clouds, or between the cloud and the ground. Okay? Well, what happens if that charge builds up and builds up and builds up? The air in between is basically an insulator. It doesn't conduct electricity until you build up enough charge, and then suddenly, and that's when you have lightning. That's a discharge. Well, every dielectric has some limit that once you exceed that limit, it actually begins to conduct, and you have a discharge. Okay? That maximum electric field is called the dielectric strength. Okay? That's how much you can put in there before you actually get discharged. Okay? Now, they left off the table. Now, none of you have a book, or some of you do? You don't. Sort of wish you did, because they have this table here that showed the dielectric constant. Okay? Now, air is effectively 1. It's just a slight more than 1, because a vacuum would be 1. Air, having a few molecules in between, will be 1.00059. So it's almost 1. Bakelite, which is basically something almost like Teflon, isn't it? No, the Teflon is later on. But it's a material, maybe somewhat similar, but not the same as Teflon. Dielectric constant of almost 5, 4.9. Now, the dielectric strength of air, it will hold up to 3 million volts per meter before it discharges. That's what happens with lightning. Okay? Bakelite, dielectric constant almost 5, 4.9, it will go up to 24 million before it discharges. So you see, you get a stronger capacitor, a higher capacitance, and a higher dielectric strength as well. Okay? Fused quartz, you can almost think of glass, but it's a little bit fancier than glass. Okay? 3.78, so that's less than bakelite, and its dielectric strength is in between air, actually closer to air than it is bakelite, so that's 8 million, okay, volts per meter. So that's not nearly as good a one as bakelite. Neoprene rubber. I want to say that's a lot like the rubber between that you would have in a tire. I'm not sure that's quite the same, but it's somewhat similar to that. 6.7, even better dielectric constant than bakelite, but it doesn't have as high of a dielectric constant as bakelite. It has 12 million, but it has a higher dielectric constant. Nylon, you know, just simple nylon, 3.4, so it's better than air, but not as good as bakelite, say, or even fused quartz. But it has a pretty high dielectric strength, 12 million. Paper, just regular old paper, okay? Put it in between your plates on your capacitor, real cheap material. It gets up to 3.4, so it's better than 3 times the capacitance, and it has 14 million. So it has a pretty good dielectric strength. Polystyrene, which is basically styrofoam type stuff, plastic, okay? Which is it? Number 6 is polystyrene plastic? I think it is. That's 2.56. Not particularly great dielectric strength. I mean, better than twice what air is, but it has a very high dielectric strength, okay? Pyrex glass, now there's a different glass than fused quartz, 5.6, so that's better than fused quartz on the dielectric constant, but also better on the dielectric strength, 14 million. Strontium titanate, what in the world is that? Sounds pretty expensive. It probably is. Why? Its dielectric constant 233.
Holy.
Whoa. Okay. Now it doesn't have that great a dielectric strength. It's just 8 million, but still, that's quite a strong dielectric constant. Teflon down at 2.1. That's just a little bit better than twice air, but it has a very high dielectric strength, 60 million. A vacuum is exactly one with, doesn't even list a dielectric strength because it can't discharge because there's nothing to discharge. Water, dielectric constant of 80, and it doesn't list that either. Okay. So, that just shows. So the simplest paper, just plain old paper, roll it in between your metal foil, you have a stronger capacitor than you had if you didn't have the paper in there. What's more, you can roll it up and you don't ever worry about the two discharging on each other. You can't roll up air, they're going to touch, okay? So paper actually helps you in two ways. Now, they didn't mention in the table oil. Oil can be a dielectric, and different types of oil can be different strengths. And what you have there is your plates are like this, and oil in between. You're guaranteed they don't touch to discharge each other. So this is a high voltage capacitor consisting of many parallel plates separated by insulating oil, and that's going to be a very strong capacitor. Okay? Or you have a metal foil with whatever your electrolyte is. Your electrolyte can be your dielectric. There's just different names for it. So here you have metallic foil, your electrolyte in between, and an oxide layer. In other words, you have a layer on one side that's an oxide, which is not a good conductor, and on this side is your metallic foil, which is your good conductor. And these form those cylindrical capacitors that you have quite often. These would also probably be somewhat cylindrical looking, but they have a fluid inside. This is cylindrical, this is white paper. Okay. So these are all types of capacitors with dielectrics. What is really going on with these dielectrics? How is it they work? Okay? This next section, 1610, is in your book it's 1681, okay, in the old edition of 1610. An atomic description of what's happening with the dielectrics. Okay? Remember, the dielectrics are insulators, not conductors. Okay? However, just because they don't move charges, charges can move within them. This is called polarization. Okay? You have a positive plate, a negative plate. You put an insulator in between. The charges on the insulator, negative charges, gravitate this way without, and the positive charges gravitate this way. It's an insulator. They aren't moving freely. They just sort of separate like that. That's called polarization. That occurs when there's a separation between the average position of the negative charge and the positive charge. Okay? In a capacitor, the dielectric becomes polarized because it is an electric field that exists between the two plates, so therefore the charges just are forced to sort of separate a little bit. The field produces an induced polarization in the dielectric material, which combats the polarization that would be in air. Here's the illustration of that.
Are you saying until 9?
Pretty close, because we did have a break. Okay. It wasn't super long, but we might quit a little early. If I come to a real good place to stop, and we're almost there, we'll stop. Okay. So, the presence of the positive charge, okay, here's the positive plate here. There's your negative plate there. Your dielectric in between. They like to make those yellow for some reason. Could be paper or whatever it is. Okay? Well, when this external field that was here anyway, it sort of separates the charges a little bit within the dielectric. They're not free to move, but they're free to orient. Before they were randomly oriented, now they orient this way. So you have the negatives favoring this side, the positive favoring that side, because negatives are attracted to the positive, positives are attracted there. So it sort of sets up this counter field, okay, that effectively reduces some of the negative charge on the metal plates. This allows more negative charge on the plates for a given applied voltage. So your capacitance increases, okay? So you actually increase the capacitance. Because guess what? Remember that earlier picture showed the 2 here and then the 1? The battery was a 2. This didn't drop to 1. You just increase the charge, okay? Because of that dielectric in between. And that's exactly what's happening here, which is increasing your capacitance, okay? And that's it. One more thing. A quick quiz.
Oh, gosh.
Consider a parallel plate capacitor with a dielectric material between the plates. If the temperature of the dielectric increases, does the capacitance decrease, increase, or remain the same?
Increase.
Increases, you say. Why? Any reason?
I would say it allows more negative charge on the plates
Okay.
for the voltage. Negative.
Here's what I would think. Now, we'll see what the answer is. You increase the temperature, these things start bouncing more. So they don't line up as effectively because they're moving more. So therefore, I think it decreases the capacitance. Watch it remain the same. Drum roll, please. Okay. 1611 A decreases.
Darn it, got
Yeah.
me.
All right. It decreases. Okay. There are some other figures they didn't show. There is a summary, goes through each of the sections. In your book, it only went through 16.8 because some of them broke into 0.1s and 2s there. The formulas are there, well worth noting those formulas. Conceptual questions there. Problems, your problems are going to be very similar to what you see on your test. So do some of the odds under 16.1, odds 1 through 9, 16.2, odds 11 through 23, 16.3, either 25 or 27 or both. 16.4 doesn't have any particular problems. 16.5, any of the odds 29 through 35. 16.6, 37, odds 37 through, 47. 16.7, energy in a capacitor 49 or 51. Capacitors with dielectrics, any of the odds 53 through 57. And then they have some additional problems which sort of mix and match all these things. You can do any of those odds, 58 through 71, 59 through 71 if you're interested. All right, now I didn't have your test run off. I will get those run off by Monday. So Monday we will start topic 17 and work on that for an hour and a half. Not an hour and 50, but an hour and a half. And then at the end of the hour and a half, we'll have 2-hour labs on capacitance. And we'll go down to the lab right next door and actually just set up some circuits with capacitors in them and just take a few measurements, and then we'll do, the rest of them will be calculations like we just did here. So I think it'll be hopefully a fairly instructive lab. Okay? So an hour and a half on topic 17, then 2 hours on your thing, and I'll have your tests run out for you too, so I'll give those to you then. I have them I have them made up, but I just didn't think, I wasn't sure we were going. Well, I was in such a rush last Thursday trying to get ready for a trip that I just found out about. I didn't have a chance to go down and have them run off or anything. So get all that done before class on Monday. Any questions? Then let's call it quits, and we'll begin. Yeah, it really was.
Do you have, I gave you my paper topic, and I was wondering, do you have it, because I forgot.
Okay. I think I probably do. If you gave it to me, I hope I kept it in order. Bye-bye. Have a good weekend. And believe me, we're going to start having 2 classes a week again. We've been supposed to, but last week it just irritated the fool out of me that they flashed it up. Okay, Megan, you said Benjamin Franklin.
Really? Okay.
What did you say?
Coulomb.
Coulomb, Charles Coulomb.
Yep.
Okay. All right, good deal. Have a good weekend. We'll see you on Monday.